Thanks for coming. I know it's an 8 a.m. start. Grab some coffee. Piyush, let's get you going on the first session of the day.
All right.
There you go, sir.
Thank you, Tom. Well, this session, we're going to explore how Aerospike works. So for some of the faces I see, you guys have already deployed large clusters. So you're going to be my helpers in the Q&A session, all right? And the rest of it who are new to Aerospike, this will be laying the foundation for how Aerospike works, so that the sessions that follow, you'll be able to relate to them much better. So that's the idea. If it is too pedantic, then give a thunderous applause and we'll break into QA, okay? So let's get started. What I intend to cover today is the Aerospike data model, how we organize data inside Aerospike, the cluster formation, and how the data is distributed in the cluster. And then we'll just walk through how the read and write transactions occur inside Aerospike. Okay? So that's the general plan. I have a good number of slides and a limited amount of time. So I will be rushing through this, and those who already are familiar with Aerospike will be helping me along. So Aerospike, as we say, is a record-centric distributed NoSQL database. This, as opposed to relational databases, which are table-centric. So we always think in terms of a record in Aerospike. In the whole spectrum of databases available, you have object databases, analytical stores. In the NoSQL world, you have columnar, document, graph databases. We shine in the record-centric distributed database. And what we offer you is speed at scale. That is the key. Millions of transactions per second is what you can achieve with strong consistency. That's the name of the game. We are strongly consistent, which means we don't lose writes, and we don't give you stale reads. So that's the mode you want to be operating Aerospike in. From a data modeling point of view, when you come from the relational world, in the table-centric world, what you get is joins at the table level from the database, right? And you are able to enter your data in the third normal form, which means entering your data, a piece of information, only once, right? And then you can do joins on the database and run your queries. This is your ACID model. The drawback with this is the transactions per second that you can run. You cannot scale it like Aerospike. When you go to the NoSQL world, in a record-centric model, encapsulation is the theme. You are putting all the data that you need from your query in a single record. So with that, you design your data model based on the queries you want to run. So that is the fundamental thinking difference when you go to a record-centric data model. Now, even though we are record-centric, we are strongly consistent, right? So let's look at our data model. How do we store your record inside Aerospike? So if you're storing a record, you need some way to access it. We call it the key, right? You're going to give us a key, and we're going to access your record with the key. And what are you going to store in the record? Data. And we'll put that in what we call bins. So this is just some basic terminology I'm introducing to you about Aerospike. You have records that you access with a key, and you put them in bins. And then we give you the CRUD operations, the create, read, update, delete. So when you're creating a record, you're going to give us the key to the server, and you're going to give us the data you want to put in, the bins. On the read, you're going to give us the key, and the server will give you back the bins. On an update, you're going to give us the key, which record you want to access, and just give us the data you want to change. Of course, you can give us the entire replace also for the entire new data, but you can incrementally change your record in an update. And in the delete, you're just going to provide us with the key, and we're going to get rid of your record. Okay? Now, every record in Aerospike has to belong to a namespace. A namespace essentially is a storage definition. How do you want to store your record in Aerospike? Okay? And optionally, you can group your records in a set inside the namespace, and that's good for data modeling. Now, if you don't specify a set, then there is the default null set that all your records will go into. Okay? So that's the organization of the records inside a namespace. They always belong to a set. If you don't specify, it's the null set. And as I said, namespace is your storage medium. Now in Aerospike, the 4 common models today are the hybrid memory model, the all RAM model, the all flash model, and then storing on a file system on spinning disk. And in each of these cases, you'll find, except for all flash, the key information, I'm calling it the information right now, the key information is stored in RAM. Okay. In Enterprise Edition, that is stored in the Linux shared RAM. But the data, if you're storing on SSDs, you can store it as a raw block device. And in performance, it almost gives you RAM-like performance in terms of read and write access. In the all RAM model, you're storing the data in RAM. In the all flash model, which was introduced last year, you can store your key information and the data both in SSDs. And in the file system model, you want to store in file system for persistence, but for performance, you want to keep a copy of the data in RAM. So that is the typical use case for storing in a file system. Okay? So that's the 4 basic concept of a namespace, and I'll get into that a little bit more. Let's explore this key info business. What is this key information? Well, when you specify your key, we take the type of your key, string, integer, whatever it may be, and the set name you specified, and we run a RIPEMD 160 hash on it, giving us a 20-byte digest. This 20-byte digest is what is stored on the Aerospike server, unless you optionally decide to store your key also, which is typically not done. So every record inside Aerospike is accessed through this 20-byte digest. We don't keep your key. This hashing occurs in the Aerospike client library, which binds to your application. Okay? So the digest is the beginning point for your record inside the server. Now, along with this digest, we also store some information about your record. It's called the record metadata. And then we will store information about where your data is located inside the server and some other information. And we call that as the primary index. So that is your primary index. It is always 64 bytes, fixed. So every record has a primary index in Aerospike that's 64 bytes fixed. So for any requested digest, the server will first find the primary index. Okay? So there is that other information, there is arbitrary information in the primary index that helps us find the primary index in RAM first. And once we find the primary index, we know the information about the record, plus we know the data location, right? And as I said, in Enterprise Edition, the primary index is stored in the Linux shared RAM. And what that does for you is it allows you to gracefully restart Aerospike and not rebuild the primary index. So that's our fast restart feature available only on the Enterprise Edition. About this record metadata, the piece of information we are storing there is the last update time of your record, the generation, it's a counter that we bump every time you update your record. And then there is a time to live, which is by default set to 0, which means your records should not expire or evict. By default, your record should live forever. Now, you have the option to set it to 10 years max if you want the expiration option. But in strong consistency mode of operation of Aerospike, we never recommend that you set your records to expire. You use the default, which is live forever. Now, this record metadata, you're putting your record on the disk. And we do this so that if we have to rebuild the primary index from the persistent storage, we can. Now, the other part in the primary index is your data location. So for that, we assign 8 bytes if you're storing on disk, and another 8 bytes for pointer to the data in RAM if you're storing your data in RAM. Okay? When it comes to the disk side, you have an ID which identifies which device in that namespace is storing your data. You can hang up to 128 devices. You have 7 bits available for ID. And then it specifies the offset, how far into the device is your record, and the size of your record, so we can go read it. So the primary index key has that information to find your record on disk. If you're storing in RAM, it's just a pointer to RAM. Now, if you're storing on device, and all your records are single bin, so it's a special namespace you have declared that all my records will be single bin and my data is going to be integer or float, then you have an option of specifying what is called data in index. So you say, I want to keep a copy in RAM of my data on the device, and instead of using a pointer, I'm going to store the data in the primary index itself. So we'll use those 8 bytes to store your integer or float data. That's called the data in index option with single bin true and data in memory true. So that kind of gives you the big picture of the namespaces now. It's really the primary index that is stored in RAM in the hybrid memory model, and the data in SSD as block writes. So there's no file system when you use SSDs. Of course, you have an option to do that, but and I believe one of the customers does it, but the preferred mode is to use it as raw block device, and then you get RAM-like performance from your storage. Okay? And then, of course, now you have primary index with both and data both in RAM. This will give you the fastest performance, but if you lose replication factor number of nodes, you will lose data, right? If suddenly if you are doing replication factor 2 and you lost 2 nodes simultaneously, then some of your data will be lost. Whatever partitions that particular node is responsive, those pair of nodes are responsible for as master and replica. Okay? So that is the downside with using all RAM model, that you run the risk of losing data, but you get the performance. So it is good for things like counters or where you need very fast access. Now, the all-flash model is really useful if you have a large number of small records, petabytes of data, and you want to save the cost of RAM. So this was introduced last year, and a few of our customers are already deploying it. So you may want to explore that if you have that kind of a situation. Of course, when you put data, the primary index on SSDs, there is a little bit of work required in choosing how many sprigs you must deploy on your configuration. And you will pay a little bit of a price in latency when you use all-flash model, but it is an incredible cost saver. And then finally, of course, we talked about primary index in RAM with data in file system and copy in memory. So with that, let's take a quick look at how Aerospike cluster forms. So in say, relational databases that are running on a single node, as your data grows, your only option is to vertically scale it, right? Add more RAM or add more disk. Why do we go to distributed databases? Because they give us the capability of expanding capacity horizontally. And the price we pay is dealing with node failures, partition tolerance. So in order to deal with it, you want to keep replica copies always. So there's at least a master and a replica copy. And that allows you to extend the capacity and achieve much lower total cost of operations. Okay? So with that in mind, how do we form our Aerospike cluster? So in this slide, I'm showing you the 2 back-end layers that help us run the cluster underneath. So on the front end, you have the client connecting, which I have not shown here, but in the back end, you have the heartbeat layer. So this is the layer that helps you form the cluster and maintain it. Okay? Since Aerospike uses a shared nothing architecture as opposed to master-slave, which some of the NoSQL databases use it, and Hadoop is an example of a master-slave architecture, where the master node knows where the data is in the slave nodes, it becomes a single point of failure. In a distributed data store like Aerospike with shared nothing architecture, the client knows exactly which node your data is on and goes directly to that node. So you get a single hop to data. Okay. But I digress from the clustering part. In this clustering algorithm, what happens is the nodes discover each other through gossip protocol. Each of them sends to the other node the adjacency list. I know these nodes around me, and they all figure out, okay, we are the cluster, and then they elect a Paxos principal, and then the cluster is formed through the Paxos algorithm. So once the cluster is formed, you're up and running, and then the only function Heartbeat has is to make sure that all nodes are still part of the cluster. And it does by sending a signal, a very lightweight signal, every 150 milliseconds. And a timeout count of 10 missed heartbeats indicates that a node is down. And so anytime a cluster change occurs, that means a node either leaves or joins the cluster, there is, again, a re-election of the Paxos principal and a new cluster is identified. Okay. So that is in AP mode. In the strong consistency mode, there is operator intervention needed to change the cluster. We'll go through that in the strong consistency class in the couple of sessions later today. Okay. Now, Heartbeat can be configured to use multicast or TCP/IP. In most cloud deployments, you don't no longer you can do multicast. So you are essentially doing TCP/IP and mesh, which we call the mesh mode. And that is the most common deployment pattern now with the mesh mode. So every node is talking to every other node in terms of the heartbeats. Okay? You can now encrypt your heartbeat messages with transport layer security or TLS, and they are exchanged between every pair. So that is how the cluster is kept intact. Now, under the other layer that I talked about, the fabric, this is where all your record replication occurs between nodes. So when you add or remove nodes and partitions have to be migrated, all that data moves on the fabric. If request gets proxied in certain situations when the cluster is going through changes, again, that travels through the fabric. So when we look at the read and write transactions in Aerospike, it's important to look at what part of your transaction is going through the fabric. Because when you're going between nodes, that's where the latency comes in, right? So fabric is an important one to consider when you're analyzing latency. So the traffic on the fabric, again, can be encrypted. And this is also the reason we like to keep all the nodes on the same LAN. If you're running across zones, then the fabric becomes a delay factor. Okay? Now, what is coming soon? This is exciting. I think they're going to release it soon. I'm not going to commit a date, but it should be probably in a month or two. Compressed data movement on fabric. Okay. So we introduced compression last year. In the implementation last year, your data was compressed as it was written to the device, and then decompressed when it was read back. In the new scheme, the compressed data will move also along the fabric. So when you do a replica write, it will move along the fabric in compressed form. So that is coming out very soon. And of course, the gentleman who pushed us to do this is sitting right here, but I'm not going to embarrass him. Well, you know, right there, Albert from Trade Desk, if you have been on the discussion forum, you probably he has been answering your questions. So, all right, so getting to the front end, the Aerospike client library is what your application binds to. And the client library does two things. It provides you all the API interface for doing all the CRUD operations and other things, but it also monitors the state of the cluster. So as part of it, when your application tells the library, hey, here is a seed node of the cluster I want to join or work on, the client library goes and opens a connection to the seed node. It can be any node in the cluster. And the seed node then provides the client library the list of all the nodes in the cluster, because it has it when it formed the cluster through that Paxos algorithm, right? And once the client library gets the list of all the nodes, it'll open direct connections to every node. So that's how the Aerospike client library talks to the server. And it talks over a proprietary wire protocol that is just a format for information exchange between the client library and the Aerospike server. Okay. And so it'll open direct connections, about 300 connections to each node by default. And depending on what the application is using, if it's a multi-threaded application, it'll typically use multiple connections. Okay. Now, how does, again, the client library find your record? We distribute all your records inside the nodes, being a distributed database, in partitions. Okay? So every record belongs to a partition, and we have 4K partitions. Now, I talked about the digest, right? You have the record, you supply your key and your set name, we hash it, we get the digest. We take 12 bits of that digest, and that identify the partition of that record. So every record, its partition can be determined right at the client library. As soon as it computes a hash, it knows which partition it belongs to. And so if it knows which node holds which partition, it can directly go to that node, right? That's how the partition is identified. So that's the key. Now, when the cluster forms, each node is assigned a partition ownership. So how does that work? Let's look into data distribution. Well, for a given partition number, we're going to hash the node ID with the partition ID and sort the value, and that gives us what's called the succession list for that partition. So if I have partition number 1, tells me which node is the first, second, third, fourth, fifth in the 5-node cluster. What is the node ID? It is the fabric port and the MAC address of the NIC card. And as some people sitting here have figured out, that can result into trouble if you don't statically assign it. You don't want to let that be dynamic. If you change your NIC card, now your node ID changes, and your partition table would change, and you could unnecessarily go through migrations when you don't need to. So a good practice is, once you have your cluster in your configuration, assign your node ID statically in the config file. So that way your partition table doesn't change just because you have to change your NIC card. Okay. So that gives you a deterministic succession list based on the node ID. Now, when the cluster forms, you have this partition table generated, and each row becomes a succession list. And because it's a deterministic algorithm, every node, once it knows which other nodes are in the cluster, can generate it locally, right? If you choose a replication factor of 2, the first 2 columns of this partition table become what we call the partition map. And that's all the client is interested in, to know who is the master and who's the replica. So that's your partition map. It's the subset of the table based on the replication factor you have chosen. Now, when the client library is tending to every node, it is asking each node, hey, who are you the master of and the replica of? And every node has what's called a version number of the partition table. So if a node thinks that the cluster membership has changed and he has a new version of the partition table, he will tell the client, my version is this. So the client only pulls the full partition map from the node or node's version of the map only when the version has changed. So it's a very lightweight operation. So it's tending to each node and asking for the partition version. If it is changed, then it'll ask for the full ownership. And once it knows each node's ownership, it figures out at the client library level who owns which partition. Okay? So that's important for the client to know which node owns which partition. So let's see what happens if a node goes out to the partition table. Let's say in this example, I have lost node C. The succession list would move to the left. And let's say in partition 1, C was the replica, A will become the new replica. A didn't have the data. It'll get the data from the master. It's called a fill migration, and it'll assume the role of the replica. And then if C was the master, B will become and C went out, B will become the master. That's in the other example, 4094 partition. And that's kind of handy because B already has a full data because it's a copy in a stable cluster. So it assumes the role of the master right away. So that's how node loss works. And if it returns back, the way we do the hashing algorithm of determining the succession list that I went through earlier, it'll come back exactly in the same position unless you have changed the node ID. So if you keep the same node ID and you come back, it'll come back exactly in the same position, which means it'll already have most of the data. And all it has to do is figure out the delta, and those delta migrations will occur, and you will be back up and running. Okay? Let me quickly mention the rapid rebalance part. This delta migration in Enterprise Edition occurs by first comparing just the metadata about the record. We talked about the record metadata in the primary index. So the rebalance is very fast. Instead of brute forcing all the records back and forth, it first compares the metadata and decides which records to exchange. And so rapid rebalance is, I believe, 40x faster in Enterprise Edition than Community Edition. Now, when you're adding a node, depending on its node ID, it's going to show up in any position in the partition table for all the partitions. For partition 0, it may show up as a replica. On 1, it may show up in the master position, and so on and so forth. So wherever it lands, it's going to get the data from the other nodes that have the data, the fill migration. And then once it has all the data, that's when the current master will relinquish its masterhood. For example, on partition 1, even though F comes in the master position, E will continue to act as the master till F has all the data. And then what happens is what we call the master handoff, and then F is ready to act as the master. Okay. Now, in Enterprise Edition, you also have the ability to do rack-aware configuration. So here in a 5-node cluster, we have split it into 2 racks by identifying in the configuration that nodes A and B will have a rack ID of 1, and C, D, and E would have a rack ID of 2. And when you do that, what happens to the partition table? Aerospike is going to make sure that master and replica are never on the same rack. So it'll first build the partition table by our hashing algorithm and look for wherever there are conflicts, which means in partition 1, let's say E and C are master and replica, and they are on the same rack too. It'll switch out C with A, the next one. So your partition table will be adjusted to make sure that rack awareness is satisfied. So that's how rack awareness works. Okay? Finally, a note on cluster capacity. If you design a cluster of, say, 6 nodes, you must always size it if a node was to be down, say, for 5 nodes. Because if ever you're going to do rolling upgrades, you're going to take one node down at a time. So you must make sure that when a node is down, the remaining cluster can still handle all your data. So this is just a quick intro to thinking about cluster capacity. And of course, our solution architect teams go through a full sizing exercise with you when you're ready to deploy a new cluster. Okay. Let's get finally into the read and write transactions. Okay. On the read side, let's see what's going on. You have your user application that wants to read a record. So it specifies the key, right? So we started with read as a very top-level description, and now we're learning everything about the partition table and all. Let's dive deeper into what's happening, starting from the user application down to the server. Okay? So you have your user application, gives the user key and set name, okay, to the client library. The library will do the hash, figure out the digest, figure out the 12 bits, knows the partition. It has the partition table that it has built by tending to all the nodes. So he knows which node is the master. And it has open direct connections to each of these nodes. So he goes to C directly, right? C will then find the primary index by doing a red-black tree search within the RAM. It starts with the partition ID as the root of the RB tree. And there is actually now a sprig ID because we have taken that big tree and broken into small trees. But let's, for argument's sake, not get into sprigs. Let's assume it's a big tree. The partition ID becomes the root, and you start searching from there. And each index entry has a right entry and a left entry and a color bit in the primary index. And you go ahead and find the primary index. So that part is very fast when you're storing primary index in RAM. When you store primary index in the all-flash case on an SSD, that's where the trick comes. You want to size your sprigs in such a way that all your search happens within 4 kilobytes, which is the page size. So you can do everything in one read, one page read. Okay? So that part occurs first at the server, finding the primary index itself. Once you have the primary index, then depending on the namespace you are in, you'll either find the data on disk or you're going to find it in RAM. And at that point, the node will return back the data to the client library, which will feed it back to the user application. But what you get here, you can see, is a single hop to data. Okay? All right, let's see what happens in create. You've given a key and bunch of data with it. Again, with the key, we're going to find the partition you should go to. And once we know the node, who's the master. So writes always go to the master, right? So you go to the master node. And in this case, once you've figured out where this primary index should go in the RB tree, and you're going to insert that index, you will write the data in the current write block buffer. So on SSDs, as I said, we're writing in blocks. So the block that is currently being written to is allocated a buffer in RAM. And the records that are coming in get stacked in this buffer. And it is periodically flushed by default every 1 second down to the device. And then finally, when it is full, it is flushed again. Okay? So that's in the overwrite mode is being flushed. So the write block is holding your records as they are coming in RAM, and it identifies the ID, offset, size, etc. Now, there is a relationship between the write block buffer and where it is stored in SSDs, so that location info works regardless of where your record is, whether it's in the write block buffer or it has already gone to the SSD, and after that, it goes in what's called the post-write queue. Now, there's some argument that it should be called a post-write cache, but that's for a different day. But it's called post-write queue right now. So that's where your data moves on the writes. Once it's written to the buffer, the master node will also send a copy to the replica node. And then once the replica node, in this case B, acknowledges the write, that's when the response is sent back to the client library and then to the user. Okay? So that's how a create work. In an update, you're just, again, sending the data that you want to update on a record. So in an update, you also have to read the current data on the device before you can update it. Because the client has just said, just change bin 2, and I have like 100 bins in the record, right? So I have to pull everything out. So the same process occurs, but when you come to the master, it's going to first read from the persistent store your data, and then update it and stick it back into the current write block buffer. And from there, it's going to send the write to the replica node. Now, when it sends the write to the replica node, it sends the whole record. It is sent as a replace. So the replica node doesn't have to go through this exercise of locally reading and updating. So the writes to the replica always go as replaces. So that's an update transaction. And of course, in a delete, all we do is delete the primary index of the key that you want to be deleted from the server. And then the threads in the device that maintain or defrag the device, they will recover this space eventually. Okay? If your data is in memory, then the RAM is freed right away. But if it is on device, it will be picked up by the defrag cycles. So that's how deletes work. Okay. Now, finally, a few more things that are available. Batch index reads, where you have your user application wanting to read a bunch of keys, an array of keys. So you assign that to the library, the client library. It's going to figure out the master for each key and rearrange your keys in groups of who the master nodes are and send each master those keys. Hey, can you read all these and send me back, so on and so forth, to each node in parallel. And so each node will start doing its work in parallel and start sending the data back. And once the client library has all the records, it will reassemble them in the correct order as you had asked for and present the results back to you. So you must have adequate RAM in the client node to handle that. So if you want to do batch index reads, that's the only thing to watch out for. Scans, that is, both scans and secondary index queries are different than batch index reads. Here you're giving the scan query to the servers, and each node runs the query and pipelines its results in 1 megabyte buffers to the client library, and you consume them as they come. So there is no order here. You'll get the results in any order, right? And then the other thing you have to worry about is if it's a long-running query, what happens if the cluster changes, if a node goes out or a node joins in and migrations occur. So you can have all those situations happening, and you have a flag to say fail on cluster change. So if the cluster changed while my query is running, please let me know. I'm going to rerun the query. So that's an option you have if that matters. Okay. And then optionally, you can do predicate filtering also on scans. Or run a user-defined function. So you can have a record UDF which modifies a record, a user-defined function running on every record part of the scan. So that's handy to do if you want to transform all the records in your database. Likewise, you have secondary index query. Works as the same principle as scan in terms of the query is sent to all the nodes, and then you get the output again pipelined in 1 megabyte buffers, and you consume them in a callback. And then again, you have the fail on cluster change option that was introduced middle of last year, again, because of a customer who insisted on having that. So if you're customers and you want something, do bug engineering, and they will give you what you want. And then you have the option to aggregate the results also using stream UDFs on the entire result set. So that kind of brings me to the end of my presentation, which is actually pretty good timing, I would say, Tom. Ready for Q&A. Any questions, folks?
Hello, I have a question about deletion. Deletion happens only in index, so this means if server starts, records are restored?
Deletion happens when?
Deletion happens only by marking it in index. So if server starts, the deleted records will be restored, yes?
No, not if you use durable deletes. So I didn't get into the details, but in our server operations course, by the way, anybody who's here, I guess they get a seat on our academy. So we go into the detail of how durable deletes work. So if you're using strong consistency mode, and if you're going to use deletes, we recommend you use durable deletes. In durable deletes, what happens is we write actually a tombstone, which means a record with all the bins set to null. It's a special type of record, placeholder. We really don't delete the primary index then. And then it's eventually cleared out. When all the existing copies of the record are removed, a certain time period has passed, and there are no migrations going on. When those three conditions are met, that's when the primary index is deleted. So you're safe from the record coming back to life. It's called zombie records. If you're using community edition, you don't have that feature available. So there, yes, you will run into issues. And community edition is AP only. So.
Hi. Yeah, my question centers around write buffers and what happens when the node on which that buffer accidentally powers down or happens to crash in the middle of a write, and what the resiliency of clusters can be when that happens to prevent data corruption.
So you have two options there. One, if you're just worried about a single node, there's always a copy on the second node, right? So that safeguards you from that situation. And then in strong consistency mode, if you're absolutely worried about it, you have the ability to commit on every write. So you can say, every time I write, I want it flushed down to the disk, period. I don't want it, it'll stay in the write buffer as it fills, but the write buffer is progressively flushed on every write also. So that's a commit to device option you have in our strong consistency mode. So you will never, ever lose a write. There is no situation where you can lose a write if you intend to operate that way.
Thank you.
Sure. So I have two questions. One is compression across the wire. So is there any overhead on the other side when you get the data to the second?
No. So when you are doing, this is not released yet. So, and I see some folks from engineering here, so correct me if I'm wrong, but I'm pretty sure on this. When you do compression through the fabric in the new scheme, that compressed record is written on the other node just as it comes compressed. So there is no decompression and recompression. That's the whole idea. You want to save on the CPU cycles. Currently, when we do compression on device level only, if I get a write, I do compression to device, and then I send the uncompressed data to the replica node. And then he does his own compression, right? And each node can run its own algorithm, by the way, but that's not what you would do in production. You want the same algorithm. We have 4 options on compression algorithms, I believe, 4 or 3. You want to run the same algorithm across the board. But the point is, when you're doing compressed on the fabric, you won't be doing this compression, recompression on the other node. You're just going to take that and stick it right there as compressed.
Okay. One more thing is the
yeah.
defrag part. You said defragging from the disk level. What is the overhead of that if you have a lot of deletes happening?
In terms of overhead, I don't know how to quantify that because there are a lot of tuning settings that you can do. Typically, we will defrag when a block is less than 50% used. So that's when the defrag kicks in.
It's not always.
Right. So if you decided to typically 128 kilobyte block, when it is less than half full because the other half of the records have been updated, now they are all updated or deleted, whatever. Even an update, when you update a record, remember we read a copy of the record, we are modifying it and rewriting in the write block buffer, which means it's going somewhere else on the device. So where it got updated from becomes a candidate for defrag. So defrags occur even with updates, not just deletes.
Any modification.
Right. So updates or deletes will cause locations in the device to become candidates for defrag. So when the whole block becomes less than 50% use, we'll take 2 of those blocks, read them into the defrag buffer, combine them right into a new block, and mark those 2 entire blocks free. That's how its defrag works. So 2 get combined to 1. Any other questions? Yeah.
Hi. So my question is about a read path. So if you have multiple replicas, how client library decides which replica it wants to read from? And also the part of a question is about zone affinity, basically. Zone affinity, because usually if you go across that.
Right. So by default, we'll read from master. Okay. So we'll always go to the master. But you have the ability to say, in the client library, if you look at the read policy options, you can say allow replica reads. Okay, so which means I can go to if the read to a master. Okay, let's begin. You have 2 questions here, really. Let's assume you are a single rack, right? You're not doing rack awareness. If you're a single rack, the client always goes to master first, and if the master is down, it'll go to the replica if you have allowed replica. So I'm talking strong consistency mode only, right? Then you say allow replica true, and it'll go to the replica and find the record. If you're doing rack awareness, you can specify which rack I want to go to first, right? So if you have two different zones and you split your cluster, as say this is rack 1, this is rack 2, every client on rack 2 wants to read from rack 2 first. So you can do that with strong consistency. It just released actually a couple of months ago, or last month. It's called Relaxed Reads and Strong Consistency. You can say, I want to go to rack 2 first. So it'll first go read from the replica, and then if replica is down, it'll go to read to the master on the other rack. So you have that option to do it. Does that answer your question?
Yeah, actually, if I don't have information about rack, I just want to make sure, like my call from a client, don't go to other zone. So I don't, let's say, have a rack information. I just want to make sure that if my client is in zone A, my all reads always go to the zone A.
Then you have to do rack awareness. Because we don't know at a client library which zone you are in. So and rack awareness is very easy. You just identify the rack ID in the configuration. Right? Any other?
I just have one quick question.
Sure.
Right here. Is there a way to segregate the heartbeat and fabric traffic?
They are segregated. They are two different.
But they're on the same card, because we've seen issues where we shut down a node.
They are. You can put now. You can have 4 NIC cards per node. Okay, so you can do 4 NIC cards. I showed in my diagram the 1 NIC card, right? But you can have 2 NIC cards. One dedicated to heartbeat, one for fabric. Let me pull that back. So that's just for convenience that I showed the same NIC card, right? But this could be 2 separate NIC cards, one handling heartbeat, one handling fabric, one handling the client side, and the 4th one you can use for XDR. So now you can configure up to 4 NIC cards per node. Okay?
Are there any plans to support compression on memory storage?
I will have to defer that to the gentleman back there on the second last row over there. Yes or no? I don't believe there is compression in memory right now, Brian. I don't think so yet.
Do you have any plans to support it in the future?
It's something maybe Ronan may be able to answer. He's our product guy, but beyond my pay grade, sir.
So some of our product team is here today, and you can.
Shane is there.
The product guy you want to talk to is right there.
The place where compression might become important in memory is when we do support for persistent memory, data and persistent memory. At that point, we will consider that.
Which brings me to one point that I was going to add in my slides, and I believe I did it or not. We just have introduced also primary index in persistent memory for Intel devices, right? So the 4 configurations I showed, the 5th one is primary index in persistent memory. So I just wanted to point that out.
Cool. Thanks, Piyush. Everybody, thank you very much.
All right.